sit and enjoy all things forest ecohydrology for a little bit in your own head and with people that you're sitting with. And then we'll do it all together with talks coming up soon.
Can we just put, can I pull up a slide just about the session here?
Sure.
Yeah.
So if someone is doing online, then should we go back here?
So if they, do you have any virtual presenters?
Well,
No,
Oh,
they're
they
all
don't have
here.
any virtual
Yeah.
presenters.
I was asking for tomorrow.
Oh, for tomorrow, yeah.
I
Then
think.
you go actually go back. And
Is Kayla here?
and make it bigger.
Kayla?
Oh, okay.
Yeah.
Thank you, sir. Hi, my name is Anukul, by the way.
Anukul? Yeah, nice to meet you. I'm Jason. Yeah. Great. Yeah.
So you're the chair for this.
Myself and Magali here. Yeah. Yeah. So you just, what are you up to today? Are you doing a little bit of this?
Yeah, I'm volunteering and I'm also upstairs.
Oh, awesome. Okay, cool. Yeah. Awesome. On what kind of stuff?
So handle.
Oh, nice. Cool. Okay. Do you work with
Oh yeah. How do you guess that?
Oh, I don't know, because he's the only soil hydrology person I have no idea at University of Saskatchewan.
Yeah,
So.
he's one of my supervisors.
Okay.
The other one is Warren Helgeson. If you have heard of him.
It's me. Yeah, I don't know. I don't know the soil science stuff too much. But, yeah.
Just
Sorry.
a second. We have then everyone goes every 45, 15 minutes, so I'll give them a 2-minute warning only. I think it's too much.
If it's too much, yeah,
it's
2
a short
minutes.
talk.
Yeah, so
So,
a minute, a warning, 10 minutes.
10 minutes.
Yeah.
So let them know about that.
Yeah, that sounds good. And then, do we know that these are all, like, I know these are all in person. I made a little announcement for Kayla. I don't know if anyone's listening, but I haven't met Kayla yet.
Yeah, I can ask.
Okay, yeah.
Hi, just checking. Is Kayla here? She's one of the presenters. We're just triple checking. All right.
Talks on the board.
Yeah, we'll just, so just put it here. This is since we have a couple minutes, this is the planned session for today. As Jason mentioned, we had one oral that was withdrawn, the first one. So this is the planned schedule. And we also have some posters related to our session tomorrow. So please stop by, talk to the poster presenters related to the session as well.
Do you know, is there, like, I didn't even think of there being, like, remote presenters. Would Kayla be a remote presenter somehow that we weren't aware of?
Is he mentioned somewhere?
I don't think so. I think Kayla's thing is on the drive.
We can check.
Yeah. Yeah, that one.
Not sure. Well, there's something
Yeah, exactly. Yeah.
no stress.
Yeah. It's just, I didn't think of there being remote presenters until one of the people mentioned.
So, Jason, look at this.
Oh.
I have to use my phone for that awkward thing, but I may do 3 minutes and 9 minutes.
Sure.
So yeah, before we know, to just give quick mention this, that we're going to be cases. And
Oh, yeah. Here, do you want, I can do that. I'll do that. It's right there.
Oh, okay. No.
That it's so nice to hear chatting and everything like that. But maybe we'll start to get this get this lined up to go. Welcome, thank you very much for everybody coming to our what's becoming a reoccurring Advances in Forest Ecohydrology session. I want to just recognize our wonderful co-chairs. Two of them couldn't make it today. Or to Saskatoon, Audrey Maheu and Sheena Spencer. But we've got Magali here, Nehemy, who's co-chairing this with myself. Jason, I'm Jason Leach. Yeah, we've got a great session. For presenters, Magali is going to be the timekeeper. She's going to give you a 3-minute warning, and that's 3 minutes until the end of the 12-minute slot. So 9 minutes into your session, You'll still have 3 minutes after those 12 minutes to do questions, which will bring us to 15 minutes, which will be the end of your time, and that's when you should really be done. Hopefully kept all the math together there, because I sure didn't. But with that, I think we should maybe get going. We're probably right on time now. Our first speaker is Michael Samoil, and yeah, looking forward to a great session. The floor is yours, Michael.
Yeah, the bigger works.
Okay. All right. Well, hello, everyone. I'm Mike. I'm a master's student at UNBC in Prince George. I'm about a year and a half through my program. So I'll be talking about my thesis. The fieldwork I've done so far has been focused on the hill slope runoff and erosion after wildfires. So we'll kind of just quickly talk about a bit of background and then jump into what my research goals were and what I've done to date and some of the impacts I hope to get out of the work I'm doing. So when a wildfire happens, it burns most, if not all, the organics off the surface, exposing the soils below. And with that, without the vegetation, the soils are prone to the wind, the rain, and the snow melt, leading to possible erosion occurring, which can then get pushed downslope and enter riparian areas. Some of the potential impacts include just altered infiltration in the soil, so just some hydrophobic soil that keeps the rainwater, meltwater on the surface. You get reduced slope stability, increased erosion, and you can sometimes get increased concentrations of harmful chemicals and metals. And with all of that going into the riparian areas, you can get changes in turbidity and nutrient concentrations, which have impacts on aquatic life. It takes many years. The picture on the left side is 1 year after a wildfire, and that is just showing a bit of grass and weeds coming in. So it takes multiple years for recovery to start to control some of that surface erosion, and then many more years to rebuild the root structure in the ground that will help create some more larger stability. So I'm focused on soil burn severity, which is specifically in the ground, not looking at so much the vegetation, but the vegetation is used as a bit of a proxy on how impacted the soil is. So the big part is that the soil burn severity is looking at organic matter loss, altered color and structure, reduced infiltration, and charring depth. In general, you can kind of view it as a slow-moving fire has the time to put heat down into the ground, which will cause more impact to the soil, burn more organic matter, likely causing more impact, while a fast-moving fire is probably just staying closer to the surface, less time to burn deep. So my research goals for this field work, we're specifically looking at how the runoff and soil erosion are compared between different burn severities and slopes. I categorized the slopes at 20 and 40%, but there was obviously a range between, went from 17 to 45% because it's hard to find exactly 20%, exactly 40 in enough places to actually work in. The unburnt control sites that I looked at were, there was a limitation with the area that I was working in, there's a lot of wildfires recently and a lot of cut blocks, harvesting. So finding an undisturbed primary forest wasn't really possible. So I kind of just found the oldest plantations I could, which were kind of cut in the 80s, planted in the early 90s, had about 30 years of recovery since. So my study area that I looked at, it's central BC. Prince George and Vanderhoof are the closest major cities, towns. And basically it's just in the middle of kind of a quiet area. It's a 2023 wildfire that burnt almost 350 kilometers squared. So my field work looked at a few different things. At each plot, I looked at or dug a soil pit to get an idea of what were was the soil composition, particle sizes, and then kind of a rough soil moisture component. And then on next was the kind of what was the surface infiltration. So I looked at the top 5 centimeters of the surface going down 1 centimeter increments just to measure what kind of infiltration rates there were, which gave a bit of an idea of how impacted the soil was, and try and see if there was a clear line of impacted soil. So just hydrophobic soil that just wouldn't infiltrate anything compared to the layer where it just wasn't impacted, so it was acting normally. And then the big part of my field work was the rainfall simulator, which is seen in the big kind of contraption. So it's kind of just a gravity-fed big water jug on top and a bunch of little nozzles that recreate rain. The plot on the ground is 40 by 40 centimeters, so it's really small, which in itself creates a bit of a limitation. You're not seeing the widespread hill slope sized erosion. You're just getting the small scale, but it still creates a good example of what is happening. My tests, I ran the rain for 30 minutes. I collected for the first 15 minutes runoff and erosion, and the second 15 minutes separately, so that I could look at how does the rates change between those 2 times, and what is eroding. Did particle size change between the 2? I used a rainfall intensity of 185 millimeters an hour, which is very high. I think for the region, it would work out to, I think it was a 100-year return for a 1 minute intensity. So just very kind of not realistic, but it was a good way to make sure there was erosion, there was runoff, there was something to compare. And with the kind of changing climate, atmospheric rivers impact this area, so maybe there's a higher chance of these more intense storms coming through. And then my plots, I would chose specifically just looking at kind of bare soil, tried to avoid rocks and organics on top in hopes of just focusing on solely the soil and sediment, how they're actually interacting with the rain. So my field work, or field plots, I got 23 total. They kind of got split up evenly between the 20 and 40% and the 3 burn severities. So onto the results. We kind of, I'll call it unsurprisingly, there is good correlation between the runoff and erosion. It kind of, they're connected. And the goal kind of was, yes, it's obvious that a runoff and erosion should be connected, but this is kind of highlighting that, yes, it is. So actually looking at both the runoff and the erosion, so each of these are the kind of color coordinated pairings are the first 15 minutes and second 15 minutes at each of the erosions. And kind of the big takeaways, no erosion essentially happened in the unburnt plots, a little more in the moderate, a little even more in the high severities. And the slope played a factor, but not as big of an impact. So maybe that came to just wasn't a big enough slope difference. Maybe a steeper slope would have been better. And then the kind of one of the interesting parts that kind of has come out of it is that the organic composition of the erosion, if we found that the first 15 minutes of the tests had the highest concentration of organics in it. There's a little bit less in the 15 to 30 minute sample. And then the control sample we took beside the plot had the lowest. So kind of highlighting that the organics are prone to eroding and get concentrated within the runoff erosion that is occurring. And then lastly, the kind of impacts of the work I've been doing in BC in general, and even just Canada-wide. The work I've been doing, there isn't really research, same kind of work being done. It's mostly been done in the US and in Europe. And then in the Nechako watershed, where the work was done, there are 15 First Nations in the area. So there's a lot of cultural significant areas, and would be nice to be able to provide what I found so that they can kind of, yes, it's maybe hard to stop the wildfires from happening, but can they kind of work with what has happened and make the secondary impacts not so bad? And just wrapping up, a big thanks to all the people who have come out and helped me with my field work, the various people that have helped me in all the kinds of ways, and especially Chislata Carrier Nation, who has supported me through the work on their land. Thank you.
Great, thanks, Michael. Fantastic presentation. We have time for a few questions. Go on over there. Yep.
So thank you, Michael. I'm not familiar with rainfall simulators.
Yeah.
So how can you make sure that the distribution of the raindrops, like the sizes, that it's realistic?
Yeah, so that's, I mean, kind of the awkward part. You can do some like calibrations with the what your setup. There are, so like, I guess my setup was built based off of someone else that did kind of the calibration work, where they found that using the like little rubber tubes that create the raindrops would produce this much energy, this size of raindrop, this kind of information. And I'm kind of going off of what they found. But then there are just, I'll say dozens of different designs. There's like sprinkler setups that have different intensities and more adjustments that can kind of provide a more maybe regional appropriate raindrop kind of information. Because yeah, there are a lot of different intensities, drop sizes, all of that kind of thing.
I mean, what about using, I mean, is there a way that you can sort of set up those similar sort of traps for capturing the natural rainfall, like setting up long-term sort of?
Yeah.
I don't know, there's complications with that kind of work.
soil, convective storm comes through, drops a lot of rain. But I mean, normally you'd expect that the wet soil should have potentially lower or better infiltration, but we didn't find anything.
Great. All right. This is the laser. Great. I think that's like that. Okay. All right. Yeah. Thanks. This is great. I realize. So today I'm going to talk about some work we've been doing at the Canadian Forest Service on modeling forest microclimates and fuel moisture. And this is a great segue from the last talk. But I was thinking that people would think, "What am I doing here in a hydrology session?" But there's a subtitle here, and it's the importance of hydrology. So I'm going to talk a little bit about how, of course, hydrology is a significant impact sometimes on forest microclimates and fuel moisture. So to provide some context, if you're driving down the highway, you see these fire danger signs. That's actually underlying that is something called the fire weather index system. And in a nutshell, it's a series of codes, and it's actually the core of it are some fuel moisture models. And the one that I want to focus on is this fine fuel moisture code model, because we're going to be doing some fine fuel moisture modeling in this presentation. And so this is modeling the moisture of those, like the litter. So we're talking about the needles, the leaves, the small twigs, and that actually those elements of the fuel bed actually are strong determinant and driver of fire behavior. So it's really important to get this right. So notice the inputs to this model is temperature, relative humidity, wind speed, and rain. And so this is a model developed in the 60s, 70s, and 80s. And importantly, there's no input about, you can't say anything about the stand, so the canopy cover, or the radiation load, the topographic position, right? So it's agnostic of all of that. So going forward, we've been at the Canadian Forest Service has been updating this Canadian Forest Fire Danger Rating System, of which the Fire Weather Index System is a subsystem of that. But one thing that we're doing is creating this new fuel moisture system. And so the idea is that we'll be able to actually model and estimate fuel moisture in a bunch of different stands, different canopy covers, different terrain positions, and so move beyond just that one static model. And how are we doing this? Well, the first step, I won't talk too much about this today, but the first step is to creating what I'm calling these screen level microclimate models. So the idea is that the input to the fuel moisture system are observations from standard open site weather stations, of which the fire management agencies have many of them. And then we're creating these microclimate models to estimate the conditions inside the subcanopies. But we're estimating RH and temperature at what I'm calling the screen level, right? So that's that 1.5 to sort of standard 2 meter height above the fuel bed. And I'm doing that because we have a lot of observations of that sort of screen level RH and temp in a bunch of different subcanopy environments, nearby open site stations. So all of this data is going into that microclimate model. And we could potentially drive a new fine fuel moisture model with those conditions, with that screen level humidity and temperature, and to actually model fine fuel moisture. But that actually kind of implicitly assumes that the gradient, that near surface gradient in humidity and temperature from the screen level to the fuel bed is kind of constant, because we actually, the fine fuels moisture is actually driven by the conditions right in the fuel bed, right? Especially the humidity, that's super important. So you're kind of assuming that gradient doesn't change across different sites and different stand types. But what we want to do is actually not make that assumption and try to come up with some way of, from the screen level humidity and temperature conditions, estimate the humidity and temperature conditions right at the fuel bed, and then drive a fuel moisture model with those conditions. And so the research questions that I want to address here is, first is, how do these near surface gradients in temperature and humidity vary across different sites? And if we take this fuel moisture model that we're developing and we drive it with the fuel bed conditions, will it be more skillful than when we're forcing it with, say, screen level measurements at that sort of 1.5 to 2 meter height? So I've been taking observations in a bunch of different stand types and topographic positions in forests on Vancouver Island. So this is over 3 years, taking measurements at a total of 8 sites. Some sort of dry, open canopy, some wet, dense canopy. The one on the right here, this is actually an ephemeral stream. I was here just in April, early April, and there was a little creek running through there. But during the fire season, of course, it's not. But there's the stream up there, but it's still quite damp, right? You wouldn't want to kneel on there because you get your butt wet. And so at all of these different sites, measuring a bunch of different stuff. Obviously, first screen level, sort of 2 meter, 1.5 meter, humidity and temperature and wind speed. But also at the fuel bed, we're measuring a bunch of stuff. One is the rain, and that tipping bucket looks like it's not level, but it is. It is. It's just the warping of the lens. So just a shortwave radiation, and then importantly measuring humidity at the fuel bed. So this is actually an aspirated shield right there. So there's a fan in the back of there pulling moisture off of the fuel bed, and there's a high quality RH temp sensor embedded in the pipe there, the same one that's in the gill screen. So being able to sort of compare apples to apples. And then, so that's getting the humidity of the fuel bed, and to get the temperature of the fuel bed, we're actually embedding, I'm sure you can't see it, but there's actually a fine wire thermocouple that's wrapped around that individual needle. And that's getting at the temperature of the act right in the fuel bed, right? So this is like the conditions that the fuels are actually experiencing. And of course, we're also measuring fuel moisture by destructively sampling these needle beds. So, yeah. So, apology. You're going to see my huge finger a bunch in these next slides. So, looking at just temperature first, and comparing the fuel bed temperature to the screen level temperature. So, here's the plot here. A lot going on. What I'm showing you is data from 4 different sites. On the top are a couple dry sites, so dry and with sort of an open canopy. The bottom are 2 wet sites. That ephemeral stream site is this 2024 wet site here. And so take you through the colors. The red is the fuel bed temperature. The orange is the screen level temperature. The black is the temperature difference, right? So a positive value means the fuel bed is warmer than the screen level. And then you can barely see it. It's small on the scale, but this is the precipitation. So some interesting stuff going on. I mean, one of it in the open sites here, the temperature differences can be quite significant, especially when, say, a sunfleck hits the region and really warms up the fuel bed, right? But then the precipitation kind of like diminishes those changes. In the wet site, however, the differences are a lot smaller, and in some cases, the fuel bed is a lot cooler. It can be cooler than at the screen level, right? So just to show that these gradients in these near surface gradients in temperature can vary quite significantly across sites, across different weather conditions. And it's interesting because you can, for these drier sites, you can actually apply sort of a very simple model where the temperature difference between the screen and the fuel bed is just a linear function of shortwave radiation. And so that you can apply a sort of one model to a bunch of different dry sites, and it actually does quite well. So I'm showing you shortwave radiation versus the temperature difference, and for these 2 dry sites, the relationship is quite similar. But when you get into even a moderately wet site or a very wet site, again, this is the ephemeral stream site, that relationship kind of falls apart. And sometimes the fuel bed temperature difference is not a function of barely a function of short wave at all, or it's an inverse relationship, right? So this is what I'm seeing this as evaporative cooling, right? So the more available energy going into a fuel bed, if there's a lot of moisture there, that's going to go into evaporation more than warming up the fuels. And so that's actually going to lead to evaporative cooling. So it's sort of an interesting but complex relationship there. So moving on to, so now no more pictures of my finger. Moving on to humidity. So I'm not going to talk about RH when I'm talking about humidity, relative humidity, because that's actually strongly driven by temperature. It's not independent, right? But what is independent is this dew point temperature. So dew point temperature is just telling you how much moisture is in the air. So this is the data coming out of this aspirated shield. So again, we've got different colors now. I apologize. Black is the screen level dew point, green is the fuel bed dew point, and the red is the difference in the dew point. And again, we've got precipitation. So just to draw your attention, say again to this ephemeral stream site, the super wet site, the dew point, the difference in the dew point. So the fuel bed is much more moist. In a lot of it is a lot more moist at this very wet site. But it's interesting, the precipitation that happens here in 2024 acts to increase the differences in the dry site, but kind of diminish them in the wet site. So again, kind of complex. And this 2024 site, I should say, has a very high topographic wetness index, right? So there's the hydrology coming into it. So again, sort of this importance of having a lot of moisture being added to the stand through the hydrology is important to the microclimate and the fuel moisture. How am I doing? Oh, good. Okay. So to move on to the second question. 1 minute. Yeah. To move on to the second question. So this is fine fuel moisture. So I'm modeling fine fuel moisture here. So the lines are the models, the dots are the observed. And the model driven by the fuel bed conditions are the solid line. The model driven by the screen conditions are the dotted line. And you can see, well, I'll jump to the next slide, but what you can see is actually the fuel bed model does a better job in a lot of cases at modeling that observed fuel moisture. So this is what it looks like looking at the model statistics across all the stands. So here I'm showing the bias, the correlation, and the root mean square error. So the take home here is that the fuel bed, the red, the results for the fuel bed is actually, the bias is generally less, the correlations are generally higher, and the errors, at least for the non-cross-validated approach, is less. But even for the cross-validation approach, the bias and the correlations are better for the fuel bed-driven fuel moisture model. So just conclusions and next steps. We saw that the near surface gradients in temperature and humidity vary significantly across sites and across like weather types, weather conditions. Evaporative cooling, topographic position, and hydrology, I think, are important factors when it comes to modeling these fuel bed conditions. And of course, this fine fuel moisture was a model more skillful when forced by the screen bed. And so, we're going to be going on sort of continuing to develop these microclimate models, continuing to develop these fine fuel moisture models, and I think I'll leave it at there. And if anyone wants to, just a thank you to, this is the group that's doing the updates to the CFFDRS and CFS, and lots of field work, so thank you to them. And if anyone's interested in all things Canadian Forest Fire Danger Rating System and updates, you can scan that QR code.
Great, thanks, Derek. That's great. We'll probably have time for one medium-sized question or two very small questions. So throw one back in. What's the dominant tree? Yeah, in those stands, it's just sort of a classic second growth Douglas fir. Yeah, but the needles, it's a little bit of an artificial experiment. In fact, in the sense that the litter bed that I'm looking at is a lodgepole pine litter bed. So these are sort of a artificially constructed litter bed because I was trying to sort of, I'm a bit of a reductionist, so I was just trying to reduce all chaos and complexity.
perhaps to a fault, but yeah.
Quick one, Daniel.
You might have said this, but how many individual units do you have racked?
Yeah, that's a good question. We generally at each site I try to at least I have sort of at least 3 of the thermocouples out there. At one of the sites I had 8 sort of closely connected, right? So I have some replication for sure. Yeah.
Thanks so much, Derek. That's
Thanks, everybody.
fantastic. So we go from the microclimate to how do we upscale some of this stuff, especially evapotranspiration. So our next speaker is Ron Shaw. Welcome.
All right, thanks for everyone for coming in. My name is Ron Shaw. I'm a PhD candidate at the University of Waterloo, supervised by Dr. Leach. And today I'll be talking about the upscale ET in mountainous area with different topographic and vegetative conditions in Canadian Rockies. So just give a little bit of background of the contents I'm going to be presenting today. So the Canadian Rockies supply most of the water from Alberta, Saskatchewan, and Manitoba, which makes them a really important area to look at. And understanding evapotranspiration, short for ET, is key for tracking forest water use. But mountain terrain and mixed forest types makes ET hard to measure and compare. So traditionally, ET are more focusing on the agricultural field or wetland, which is more homogeneous. But at the urban area, such as the study area I'll be introducing a little bit later, that the condition is more heterogeneous, which is creating a lot of challenge when we compare them. So the traditional methods, such as eddy covariance, which is a really cool instrument with just 2 hands facing to each other, they are accurate but limited in their spectral coverage. And upscaling ET with remote sensing and ground-based data could improve this to a larger scale water use estimates. So talk about my study area. I have a really great honor to work in those fantastic places in Kananaskis, Alberta, and located on a private ski resort, but they're under renovation almost for a decade, so they have less human activities happening in there. So I have 2 study areas. One on my right is the forest tower, which is a denser forest, and then on a flat slope, south-facing, and have elevation about 2,000 meters. But we also have another site called Fortress Ridge South, short for FRS. They are more spread forest, and they are like have steep slopes as well, and also south-facing. So at least they have similar aspect, but just remember they have different like forest conditions. Also, the steepness are different as well. So jumping to my method. So my method comes into 3 directions. The first is the point scale. So I have this little box. I said it's a photograph on the very top. It's a cephalo sensor that they have the probes that are attached to the tree, and they can calculate how much water transfer from the root through their foliage stemata, and then you can actually calculate the transpiration from the sensor, then scale up at a stem level. Then I have the Hale slope scale, which is from either eddy covariance or from some empirical functions with weather station data. They offer a broader coverage, but again, they're limited by the footprint area or the coverage area. And the more complicated the forest be, the less area they could be offering when they're estimating the data. So I have the Bayesian scale methods, which are involving the remote sensing, mostly my favorite part, and some physical modeling as well to provide extensive spatial coverage, but facing the resolution challenges. Yeah, like obviously you won't be able to get all the advantages from one method, right? So I'm just gonna quick jump to the results. So again, I'm still like early stage of my PhD journey. So it's all like preliminary results here, but we can still spot some quite interesting things. So here we have AET, Well, AET, which is the blue left blue bar here. We also have PET, which is the orange lines over here. So AET is short for the actual evapotranspiration that's measured from that eddy covariance equipment. And The PET is calculated from the Pendermonte's empirical functions, which you put some weather station data in, like such as wind speed, temperature, net radiations. You got the potential ET that corresponding for if they don't have any water stress, how much evaporation it can be. And we have the transpiration, which from the is a green bar from the flow sensor. So you can tell that through the whole season that PET is overriding for the AET and transpiration, and at some point that they are even lower than the transpiration, which means that there is some water stress happening in the forest that you won't be able to evapotranspirating as much as it could. And also there's a time that they're having the most intensive stress that transpiration is clearly dominating for the evapotranspiration part. So just another slide showing the cumulative transpiration AET and PET. So the blue is the PET, orange is the AET, and the green, which is pretty new, is the evaporation. So pretty much I use the AET minus the transpiration, which is red, and then you get the green. No, sorry, it's the opposite. Evaporation is red, sorry. So the transpiration is generally higher than the evaporation through the season, which makes sense because the dense forests and the forests they have like deeper roots, they have like shade effect from the canopy, so they're providing they're kind of slowing down the evaporation effect, especially during the drought season. So when we break the evaporation and the transpiration apart, and we connect them with two major elements related to water during the growing season. One is the soil moisture, which is the blue line in both of the graphs. Another one is the precipitation, which is the green bar over here. So you can find some interesting things. So the first panel on the left side is the transpiration here. So you see transpiration going down pretty corresponding to the soil moisture. However, once the soil got dried, because they are largely depends on the snow melted water. Once they are dry, they are highly depends on the precipitation through the season. And you can see they got like fade up during the larger precipitation event, but also they're not corresponding very well because it's a dense forest. They have like different roots, so even they don't have enough water just for the precipitation fade, they still have the opportunity to get water from deeper roots. And also the evaporation obviously is more sensitive to precipitation compared to the transpiration. And then some remote sensing work. So at Forest Tower, dense forest, we have the ecohydrology planted here for a longer time. So I'm able to compare the remote sensing data because I got enough days. So this is from Sentinel-2 data, which is about 20-30 meters resolutions, and with different indices. So I have NDVI, ENDVI, MDI, VARI, and then JNDVI. So all the NDVI related indices have like a more significant relations when compared to the evapotranspiration, which have like a higher R square. That the highest one is 0.31 with a lower RMSE. However, RMSE is not low enough, which indicating remote sensing itself might not be the only reason, not be the only element to estimate evapotranspiration. And here is another aggressive approach I did. So just combining two different satellites by using some tricks to combine their bandwidths. So this is a combination between combination of Sentinel-2 and Planet satellite data together, and just with the different remote sensing indices. So the blue one is the ET through the growing season, and the red one is the smooth remote sensing indices curves. So you can see at some year that they are really corresponding to each other, like up and down pretty much at the same time. But at the other years, they are less related to each other, which means just considering about remote sensing indices, there are also always more elements that you should consider, such as like precipitation, net radiations, and I can keep going forever. So there's something we should consider about. So other than just directly use remote sensing to estimate ET. Okay, so jump to my next study area before I completely forgot. Okay. So I have another site called Fortress Results, short for FRS, and they are a little bit different than the Fortress Tower, more sprays. They have the chrome holes, which are small tree branches, have like around 2 meters high, and also have the tree islands in the blue, have like higher trees of 3 to 8 meters. And the EC Tower was installed in 2024 with a challenge of capturing ET, because we don't normally have like a lot of experience of working on steep slopes with ET. So similar results with the previous ones, but now we also have the physical data from the physical-based model, CRHM as well. So you can see the through the season, there's still like great water stress at FRS as well. It's even larger. And also because it's a more spread forest, the transpiration is not dominating anymore in the beginning of the season. But when there's a larger water stress, the root, even if they're not so deep, this can still pull some water from underground. So we have some catch up a little bit in the later season. And similar results here. So the evaporation is actually dominating this time other than the transpiration. So you see the light blue here, they are overriding the transpiration, which is the green here. So which means the less tree densities and less contribution from the transpiration. So similar here. The soil moisture drop after snow melting period is over, and all the first precipitation even is in the growing season. And the transpiration shows shows strong sensitivity to precipitation inputs and soil moisture levels. And evaporation remains active even during the dry periods, which means that although there is like not a lot of trees that providing the transpiration, there's still like a grassy like fair weeds in the area, and they're actively growing during the season, and they save some like precipitation like from the leaves and evaporate out. So down to my discussion point. So this forest presents higher ET rates in general due to the capacity of holding soil moisture with their deep rooting system and climate state, versus the spread forests have a lack capacity to do that. And ET monitoring on the slope has challenges due to the wind speed, footprint calculation, and solar radiation components, which requires further investigation. Remote sensing indices have show strong relations to estimate ET. However, there's still further things to consider about it other than just use it to direct compare. So to upscale ET, it's essential to combine advanced remote sensing techniques such as using high resolution satellite, such as Planet. I could do a better job on that. And the drone data with the physical models, which is we are currently doing, and hopefully present like next interview once we have the data. So just quick acknowledgement. I would like to acknowledge that work was conducted on the Treaty 7 territory, the traditional territories of Blackfoot nations, including Sikiska, Kani, and Kainai, and Tsuut'ina Nation and Stoney Nakoda First Nations. And my work has so far been supported by Dr. Rich Pachon and Dr. John Pomeroy from University of Saskatchewan. And the data analysis and fieldwork work helped with Miroslava, Ivy, Lindsay, Eric, Kate, and Savannah. And thanks for listening. Open questions.
Thanks for that. That's fantastic. Thank you so much. We have time for a couple questions.
Yeah.
Thanks for your talk. I was just wondering if you looked at any of these like newer flux variance partitioning methods to get G and ET from the equivariance data alone.
Yeah, these are definitely on my plan book, like to do in the future, because I want to dive into more complicated like physical based models. But there are definitely some like physical models that developed from the forest side. I'm down to test them out as well, but once I get a chance. So far I only use the CRHM provided by other researchers and also the permanentes so far, but that's definitely on my list. Thanks for asking that. Yes?
Would you imagine sort of applying this method to, I mean, there's lots of other sort of flux measurements at a bunch of different sites across Canada, you know, like the flux system. Would you imagine that it could be applicable to older data sets?
Yeah, that's a good question actually. So it's always a big limitation of how to extend your model or how to extend your research in the other areas. Because even we sometimes we run into the problem that we develop the equation in here, but we applied it like 100 meters away, then it's different. So I'm totally open to apply this on any data available, like with the FluxNet, for example. But it has to be similar conditions as well, like alpine forests have similar like microclimate and everything. But yeah, I would really wish to get a universal like model out. That would be a big breakthrough. But keep my luck on.
Wonderful. Thanks so much for that. That was fantastic. Sheena's here! Hey, hooray! This is fantastic. Oh, what a relief. I'm glad you're here. Last two talks, we're going to go into the trees a little bit more, I think. So we've got Kayla Wicks. The floor is yours. Looking forward to it.
Hi everyone, my name is Kayla Wicks and I am a PhD student at the University of Guelph with Dr. Aaron Berg, and I'm very excited to be able to share with you all today a little bit of the work I've been doing lately, and that's investigating temporal relationships between soil moisture and plant water content using impedance probes in the boreal forest. So a little bit of background, the boreal forest is basically forms a circumpolar belt of semi-continuous mixed and coniferous species, and about a third of this forest is within Canada here, so it's really important to Canada. And in recent years, we've seen an increase in the amount of forest fires and droughts that we've experienced here in Canada. So Canada averages around 2.1 million hectares burned annually and about 8,000 wildfires, and these intensifying its disturbances are due to water limitations increasingly threatening this region. And so emerging methods for looking at some of the moisture dynamics here is a lot of times like remote sensing, particularly when we're looking at rural regions and broad scale applications. So microwave remote sensing enables large scale soil moisture monitoring for nearly daily temporal coverage. And some of the challenges with microwave remote sensing is actually being able to separate the vegetation and the soil moisture contributions from these signals, particularly in densely vegetated areas. And a lot of this is due to limitations in ground data or in situ networks, which can hinder model validation. And so some of the gaps in these validation campaigns, so we've pushed towards creating these large validation campaigns, is thinking about how can we separate some of these vegetation and soil moisture contributions and try not to lump together certain species. So this figure is actually from a paper by Nehemy and al. It's from 2015. And what they did was they used impedance probes or soil moisture probes, and they put that in the trunk of a tree to measure the xylem dielectric. And what they found was in two species, oak and maple, which often are lumped together as hardwoods, they have very different hydraulic strategies. So that was two components of that paper that kind of drove this research. And then another paper by Holtzman in 2021 suggested that also when we do these validation campaigns, we're often focusing on the stem water content and not necessarily the moisture that's in other parts of the tree, including the canopy and primary and secondary branches, particularly when we're relating this to vegetation optical depth, which is a remote sensing technique for looking at the vegetation water content. So these two studies kind of fueled my research objectives. So for my project, I'm looking at first trying to understand the relationship between xylem dielectric and soil moisture from these impedance probes, and then wanting to compare the hydraulic strategies across several boreal tree species. So we're looking at jack pine, black spruce, and aspen, and then investigate the seasonal moisture storage changes in the branches and leaves throughout the summer growing season. So my study area takes place in central Saskatchewan. It's just north of Candle Lake. And this was the data collected from my project took part in a much larger project, and that was the SMAPX 2022 Boreal Field Validation Campaign. So this area has cool subhumid continental climate and average annual precipitation of about 428 millimeters per year. A little bit more information on that campaign itself. So all of our sites were chosen to fit within a single SMAP, or soil moisture active passive pixel, so we could relate it to microwave remote sensing. And this study area has 35 in situ soil moisture network stations, 25 of these were equipped with an additional hydroprobe that was put into the trunk of a tree because they were forested. And our dominant species here include black spruce, jack pine, and aspen. In terms of our sampling regime, so at each of these network stations, which you can kind of see in that top photo, we have 2 soil moisture probes. So the first probe was placed in the organic layer at a 5 centimeter depth. So most of our sites have an organic layer. And then the second probe was placed 5 centimeters below the organic and mineral interface. And then we also put one at breast height horizontally into whatever tree species was closest to our station. These impedance probes are basically monitoring the real dielectric constant of whatever medium it's positioned in at hourly intervals. And then we also took destructive samples of the primary and secondary branches as well as the leaves from the adjacent trees. And we did this on alternate days for 2 weeks in June and then 2 weeks again in August across all 35 of those sites. And 25 are included in this study. So moving into my results. So this is just a comparison of just looking at the averaging from all of those probes across all of our sites. So it's just a time series of the dielectric content. So at the bottom, we have precipitation. And then the red and yellow line are our soil moisture probes, and the green is the xylem dielectric. So as you can see throughout the season, there's a slow dry down. And then as precipitation events occur, the soil moisture is getting wet, obviously, because it's a precipitation event. And the xylem is responding to this less and less throughout the season, but they do respond to the peaks of precipitation. So one of our questions that we wanted to investigate was, could we capture a lag time in between the moisture uptake in the plant and what we're seeing in the soil moisture? And what we found in the conifers, so black spruce and jack pine, was that there was virtually no lag time, or at least it was not captured at hourly intervals. And then we did have a positive lag time of 1 hour for aspen. In terms of, this is just a box plot comparison at looking at the species moistures trend just for, across like black spruce, jack pine, and aspen. So the first box of each of the colors is the xylem dielectric. So the black spruce and jack pine were very similar in terms of their RDC, but aspen was far wetter. And then looking at the middle and the last boxes of each of the colors, those are the soil moisture probes. So black spruce has much wetter soils, and then aspen and jack pine have much drier soils. And we also measured the diameter at breast height, so I just added that in the corner there. Black spruce and jack pine were very similar at around like 11 to 12 was their diameter at breast height, and then aspen was much thinner at 7. So kind of where I'm at in this project now is I'm looking at the soil water potential to tree RDC, and I've just like created plots for one example for each of the species. So for jack pine, we see that there is a clear linear relationship. Things get a little bit more complicated with black spruce. So it's colored by the season. So our darker points are early in the season. Black spruce is like wetter, and then throughout, as it dries down throughout the season, our soils get drier, and then the tree RDC drops toward the end of the season, but our soil water potential is higher. And then aspen, we have like a nice clear linear relationship. So what we're trying to show here is that not really sure yet what the heck is going on there. We have to do a lot more research and figure out why we're seeing some of those differences between the jack pine and black spruce in particular. But what we can say is that based on where we're at so far, there are clear hydraulic differences between these different species, and that needs to be taken into consideration when comparing it across broader spatial areas. So in terms of my summary, we found that there were strong correlations observed between the xylem dielectric and the soil moisture probes. There was minimal lag time between xylem and soil RDC at an hourly scale. These species have distinct hydraulic strategies, and my next steps will be to investigate the seasonal moisture storage changes in the branches and leaves and integrate some of those destructive samples. And then eventually, the broader, application of this would be taking into consideration our species distribution across that entire SMAP pixel instead of simply lumping together conifers and mixed vegetation. Anyway, in terms of participant acknowledgements, so this data came from a much larger project. So I'd like to thank everyone who came out and helped sample to collect this data from the University of Guelph, University of Sherbrooke, Toronto, QTR, Carleton, NASA JPL, University of Sask, City College of New York, and Environment and Climate Change Canada. Thank you all for listening.
Thank you so much. That was awesome. We have time for a couple of questions. Right over there.
I have a question from the slide on slide 130.
This one, yeah.
We can see 3 groups that are selected. Can you elaborate that?
Yeah. So we're not really sure at the moment why we have like these 3 groups. I think like my next steps is I want to take that site in particular and compare it with like some of the precipitation data, just to see if those like gaps or breaks in precipitation, and then also compare it with like a time series, because I think like I'm just gonna go back to the slide. So as we go through the season, we see that the tree RDC in green is kind of responding less and less to these precipitation events, but the soil moisture is still peaking pretty dramatically. So I'm wondering if like as we're getting toward September, which is the lighter colors on that black spruce plot, that the soil water potential is increasing because we had a precipitation event, but perhaps like the tree is not responding as we're getting into like the cooler months. So I need to do a lot more research on black spruce specifically and kind of dive more into like the ecology on that. But yeah, thank you.
Any other questions?
Yeah, thanks, nice work. How easy would it be to convert your RDC into like actual moisture units?
Yeah, so I was trying to do that with like moving toward like the soil moisture space of the soil water potential. Thankfully, most of our sites are sand, so I was like using Brooks and Corey equation to kind of convert that. I think like, but in terms of putting like the tree RDC into like moisture, unfortunately, like we didn't do like a whole calibration for the tree specifically before we put them in, and that was just because like we found that using these probes is a good alternative to like sap flow sensors because they work just as well. But when you're putting them in the tree, taking them out, you basically are destroying the probes most of the time. So they're really good for like long-term measurements. But yeah, we didn't do calibration because we didn't want to like kiss our sensors goodbye beforehand. So yeah.
You did such a great job with time management, so you're going to get another question. I'm sorry.
Yeah, I was just building on this. I'm curious too, and then I see now that it's all sand, but I was wondering if there is any influence of the soil itself on this response, because black spruce, we don't usually find that in sand soils. And then I wonder if this has anything to do with that. Because jack pine, yes, but then whether there's texture specifically in the snare is influencing that response.
Yeah, I need to like definitely deep dive in that. I think another thing I want to like take more into consideration is like the black spruce sites. Those are typically far wetter, but I'm wondering if that's because most of our probes have like such a thick organic layer and they're kind of in the middle, and then versus jack pine, some of those plots like the organic layer is so minimal that top probe is really in like a mineral layer. So I think I'm gonna deep dive into that more. Yeah. Thank you.
One last question. The larger project, is it this validation project? Is this primarily focused on the boreal, or is it looking at all forest types across Canada or range? Yeah.
So there's been several validation campaigns. So I was part of Dr. Ehrenberg, he was the one who kind of like was running the boreal one. So the data from this project is from the SNAPEX 2022 boreal campaign. That is out now 2 weeks ago, I think it was out. And that data is open access. So if you go to like IEEE, you can get the RDC data as well for the network. Yeah.
Thank you so much.
Thank you.
That was fantastic. Thanks. All right, our last speaker, she needs no introduction. Go ahead. Magali.
And I won't manage the time because I'm the last one, so you guys are stuck with me. I'll just pull up the presentation. I'm kidding. I will do. All right. Yeah, thanks everyone for coming. My name is Magali Nehemy. I'm assistant professor at Trent University. And today I'll be talking about transpiration source water in the Amazon. And the title of this talk, Variability in Transpiration Source Water, is influenced by embolism resistance across topographic gradients in the Eastern Amazon forest. Quite long, but it's the main message here. So if you capture this is what I want to share with you, and I hope that at the end you're thinking more about how hydraulic traits itself are quite important to understand transpiration source water and potentially transpiration age. But before I start, I would like to acknowledge the land and its people where this work took place. I would like to first acknowledge the land, the Amazon forest, and I'm grateful for the Amazon for all that it provides. I'm also grateful to the indigenous people of this land, particularly the Tapajós forest, and specifically to the Mundurucus for welcoming us to their home, sharing their knowledge about the forest, and teaching us how to cultivate a relationship of respect and care for the land and Mother Nature. I'm also grateful to the Anishinaabe people. I'm at Trent University, which is located on what's currently known as Peterborough, which is the traditional and treaty territory of the Mississauga and Anishinaabe people, and I'm grateful for their care and teachings about the land. And I'm also grateful to all of these people and the funding agencies that supported this work. So there's a lot of people involved, and doing field work in the Amazon is not the easiest thing. So I'm grateful to all of them. So we know that transpiration contributes to up to 70% of the dry season rainfall in the Amazon. And this contribution is particularly important in the southeastern part of the basin, where this contribution can be larger and more significant and impact forest resilience. So it means that there's a lot of moisture that is returned and recycled to the atmosphere by the plants itself, which means that the forest is actually mediating drought and the drought impact, and therefore impacting the vulnerability of the forest to climate warming and climate change. And we're actually seeing this importance and the vulnerability of the forest to changing inland cover. So there's a recent study showing that the dry season is getting drier in the Amazon, particularly in areas where we're seeing higher deforestation rates, and we're seeing reduced rainfall amounts in the dry season. So now that we know that transpiration is the source of precipitation during the dry season, what is the source of transpiration? So it's kind of a chicken and egg question here, but we're really interested in understanding where is that transpiration coming from? Is that from shallow soil layers, deep soil layers? Is it recharged during the dry, or is it recharged during the wet season? And what are the drivers that are changing this transpiration source across the landscape? While we know, or we have actually little knowledge about the empirical relationship between hydraulic traits and transpiration source, we know that some hydraulic traits, for example, the hydraulic safety margin here, I won't get in detail, but it's really important and a key trait that can explain forest mortality. So we have this understanding, and it's not only across one biome, but across multiple biomes, and is a great trait to explain forest response to drying soils. We also know that P50, which is known as embolism resistance, is really good to explain trees and species response to drying soils. So it explains that species vulnerability across the landscape. So in this recent-ish study, we show that the variability of drought resistance between hill and valleys is actually explained by P50. So at the Tapajós site here, we have the P50 values. For those that are not familiar with this, is actually the water potential where trees lose 50% of their hydraulic conductivity. And you can see that on hills, the P50 values are quite negative, which indicates that those trees are quite drought resistant. So they can deal a lot with lower moisture conditions. But when we compare to the valley sites, you can see that P50 values are quite close to zero, which again indicates that those trees are not quite suitable and cannot handle a lot of drying conditions quite often. And this is not particular to the Tapajós National Forest. We saw this across other sites within the Amazon and also in a savanna site. And we're not only the first ones to show this. So this is a known trait that can explain this drought sensitivity. So now that we know that traits are really great to explain how trees respond to water availability, how does transpiration source water vary across the topography and species with different embolism resistance? So to answer kind of these two questions now, we're leveraging the Tapajós National Forest and those two sites, the hill and valley, and we conduct our campaign during the dry season. The Amazon forest is quite heterogeneous. It's not all rainforest. You have areas with very high seasonality. So for example, this eastern part of the Amazon, you can see that precipitation drops to below 100 millimeters a month during the dry season. And we conduct our sampling quite right in the middle of the dry season. So basically, at each site, hill and valley, we had some overlapping species, sometimes overlapping genera, and we were collecting the xylem. I mean, people that were quite skilled, they were going up the trees, and I was just down there waiting for their branch to drop, and then quickly chopping that wood and putting in a vial for later extraction of xylem water. We're also collecting soil, and then I can say we, because I was collecting that part too, for also cryogenic extraction of the water. We collected stream, groundwater, and precipitation. Although it's the dry season, we do see precipitation events. And then for the long-term precipitation signatures, we use the GNIP station nearby and also compare to the modeled precipitation for the specific geographical location at our sites. And as expected, you can see there's the composition of precipitation being quite enriched during the dry season and then more depleted during the wet season. So what do we found? We found that the majority of transpiration is actually coming just from the first 50 centimeters of the soil profile. And those first 50 centimeters, they reflect the mean average dry season precipitation values. We also see a slightly higher moisture at those shallow soil layers. And you can see that on the hills, there is an overlap of the xylem water with mostly the dry season shallow soil layers that is storing that dry season precipitation. And we use a mixing model analysis to compute the percentage, and about 85% of the transpiration is coming just from those first 50 centimeters, which is the opposite, which was expected because those trees have quite dimorphic roots, so they are capable of accessing deeper soil layers, but doesn't seem like they really need it. Whereas in the valley, you can see this quite wide distribution of xylem water and overlapping both deep and shallow soil layers, although there is still a 45% contribution from the dry season rainfall stored on the shallow soil layers. You can see also, just pointing out, the xylem water does overlap with the bulk soil layer distribution, so there's no like a weird anomaly here within fractionation is evaporative fractionation within the soil. You can see the profile of the bulk soil and the more mobile water too. They're overlapping quite closely. So this is to say that there is uncertainty within analysis, but things are plotting where we expected regarding to the xylem water. And then we also found that the embolism resistance here, the P50, can actually help us to explain this pattern that we observe in both hill and valley. So if we look at the P50 value for the hill, more negative means more drought resistant, and more drought resistant, more shallow water use we're seeing here, like more of the transpiration is coming from the first 50 centimeters of the soil, because they can drop their water potential and kind of pull the water from that dry soil layer. But then in the valley, we see an inverse relationship here, where both are quite significant and can explain about 50% of transpiration water use. But here, the more negative P50 reflects more deeper water use. And there's literature showing that trees that are growing near the water table, they are hypoxic, and those hypoxic conditions, when they suffer those conditions, their response is kind of a drought. So species that are able to uptake water under those low oxygen levels, they are also showing this higher embolism resistance. So basically, the take-home message here is that in the Eastern Amazon forest and supporting some of the literature, we're seeing here that the trees can quickly produce their own rain when they need it the most, and they're quickly returning the dry season precipitation back to the atmosphere. And the P50 helps us to explain this spatial variability in transpiration water source. But then the question was, is there enough really rainfall during the dry season to support transpiration? So a quick kind of back of the envelope calculation here, by upscaling the results to the basal area of the dominant species that we sampled, we reached to about 69% of the transpiration is coming from the dry season 50 centimeter shallow layer. And if we look, my time's up. In 12 minutes, I'll take this last one here just to share that we know that transpiration rates increase to about 90 to 120 millimeters per month during the dry season, and precipitation average about 60, which represents within this 50 to 67%. So yes, there is enough, and the trees are quickly putting back the water back into the atmosphere, which is contrary to the belief that they were then tapping to much deeper resources. Yeah, that's all. Thank you. And you can apply this in Canada. It's not only the Amazon. That's our next, step. Yeah.
Along those lines, how is within the so I've seen the trees in the valleys are quote unquote less are more sensitive to dry conditions. But do they have to worry? And then, so, because they're in the valley, they don't need to worry. But how is climate change manifesting in this sort of landscape? Like, or what sort of changes in the hydrologic cycle are you seeing there that may sort of influence how some of these relationships move forward into the future?
Yeah, I guess the dry season's getting drier, so water table levels are dropping. Perhaps we need those measurements to really see that. Valleys represent about 36% of the Amazon, so most of the trees are on hills. And hills, they're able to actually uptake the drying soil conditions and uptake water. But yeah, the trees on the valley will have to adapt, and there are some recent papers that showing that they can adapt. So the question is, how much can we push the envelope of those P50 and safety margins? And that remains to be seen. Yeah. Yeah, I think would be interesting. The Amazon is quite diverse. Even sampling the dominant species, we got about 40 and 20% in each site. And in Canada, we have the advantage of having homogeneous landscapes. with one species. So it would be interesting to really understand if we can see this pattern and if the trees really show within the same species, which we see here, same species in the valley and hill showing contrasting P50s. So applying here to understand. And and there potentially we can use P50 to actually understand transpiration age. So that would be next steps. Yeah.
Wonderful. I think that
Yeah.
brings us to time.
Yeah.
Thank you. Thanks to all the wonderful speakers today. That was fantastic. I learned a lot. That was great. Thank you all for making the time to come to this session. We love forest ecohydrology so much, and we're so glad that you want to come and talk about it too, and learn about it. And I hope you all enjoy the rest of your where are we? Conference. But maybe it is a conference. I don't know. But enjoy the rest and go have some lunch, and we look forward to seeing everybody
Next year. Yeah.
next year. Thank you.
We can see that.